In this video you will learn who Gustav Kirchhoff was and what the first of his famous rules for the behavior of currents in electrical circuits says. You will also learn how charges behave at junction points in a network and how you can easily calculate missing currents. And finally you will also learn what Kirchhoff's first rule means in practice to you and to the circuits you design. And as always you will get a summary of the most important facts from this video at the end, so stay tuned. And my name is Andreas from the Fearless Engineer, and here we go. Now, before we dive deeper into this concept of the junction rule, let's look at a broad definition, for example, one we can find on Wikipedia. There it says that this junction rule, this law, states that for any node, which is a junction in an electrical circuit, the sum of currents flowing into the node is identical to the sum of currents flowing out of it. So we are talking about charges, we are talking about a current flowing through a circuit, and the junction rule tells us something about the behavior of the current, the behavior of the individual charges which meet at a certain point in this circuit, at a so-called junction. And before we dive deeper, let's quickly recap some items which we have talked about in previous videos, which we will need here in this video. And the first is basically Ohm's law, and it says that the current flow, which is caused by a potential difference, voltage between 2 points, and the resistance of the conductor through which the charges flow. So basically Ohm's law, which states that voltage is the product of resistance and current. And secondly, in an unbranched circuit, the amount of charge is the same, is identical everywhere. If we have no branching off of parallel components, every charge, if you observe a charge moving from the negative to the positive terminal, this charge will pass through all the components in the unbranched circuit. This is opposed by parallel components in another circuit which has branches, and we have seen that already in the experiments which we conducted in the last video of the electronics challenge, where we observed what happens to the current flow, what happens to the voltage drop in such a parallel setup. And in this video we will dive deeper and look at these phenomena from a more theoretical viewpoint. We will discuss the famous junction theorem, which answers this question of what happens at so-called junctions or nodes in a circuit where the moving charges split up. But first, let's talk about who Gustav Kirchhoff actually was. He was a German scientist in the 19th century, and he was apprenticed with a very famous mathematician called Carl Friedrich Gauss, which you surely have heard about in mathematics class in school. And he formulated, Kirchhoff, still as a student, two very fundamental rules of electricity regarding the behavior of current and voltage in a circuit. And they're so famous that in Germany there's actually a postal stamp on which you can find these two rules and also his face and his name. And the first of his rules describes the division of currents at a junction point in a circuit. So the first rule is concerned with the splitting up of charges at a junction point. And the second rule describes the distribution of voltages across components which are connected in series. So first rule about parallel components, the second rule about components connected in series to each other. Now let's look at this simulation here. What you can see here is a circuit which is powered by a voltage source, which you can see here on the left. The longer bar is the positive terminal, the shorter bar is the negative terminal, and the current flow, as you can observe, follows the technical current direction which we have talked about before. Now, when the electrons arrive at a junction point, for example this one here, the current flow is split up, right and to the top, and you can see that the current flow splitting up to the right is smaller, indicated by the lower velocity of the yellow points here when I started once more, and also they are more translucent. It's at 3.98 milliamps. This is smaller than the current flow to the top, which is at 15.91 milliamps. And at this point here, and this junction point in the middle, we have four branches meeting. We have two branches with incoming currents, which is the left one and the topmost one here, and we have two branches moving out of this junction point, one to the right and one to the bottom. And the right one here is at 8.5 milliamps current outbound, and the lowest one here is 11.36 milliamps, also current flow outbound, and the other ones, the green ones, are have an inbound current flow. And interestingly, if you compute the sums of the inbound current and the outbound currents, they are exactly at the same value, 19.89 or 88, almost the same milliamps. And this is basically what the junction rule tells us, that the sum of the incoming currents into a node and the sum of the outgoing currents out of a node is identical. And now let's look at this observation from a more mathematical formal viewpoint. And this is exactly what Kirchhoff's first rule does. It states that in each junction of a circuit, which is such a center point here, the sum of the currents flowing into the junction point or the node is equal to the sum of the currents flowing out of it. So we can formulate this by using this sum notation here. The incoming currents are identical to the outgoing currents, which is the overall amount of currents is identical to 0 here. And Kirchhoff's first rule describes the conservation of charge in the electric circuits. All the incoming charges must go somewhere. They cannot simply disappear, which is why they split up onto the outgoing branches. Charges are never lost in a circuit. Now let's take a look at the practical significance of Kirchhoff's rule. Firstly, Kirchhoff's first rule, the junction rule, can be used to calculate missing currents in a network. And secondly, from the junction rule results the formula for the parallel connection of linear resistors in a network, in a circuit. And thirdly, the junction rule, it can be used to calculate how currents are divided at junction points depending on the resistance values within these branches to which the junction leads. And in the next module, we will look at the parallel connection of resistors, and also we will derive and look at the application of the current divider rule, which helps you find the amount of current which passes through the various branches of a network and which is based on Kirchhoff's rules. And this is all from for this video for now. If you have any questions, leave me a comment down below. Also, if you have ideas for future videos, leave them here. And this is all from me for now. I wish you a nice day. See you next time here on The Fearless Engineer.